Hello, in this video, I'm gonna introduce how this principal component analysis is derived. So assumption. So here we have X is a design matrix. And which has dimension n times d. We have the sample size is n. We have d features. And this is not regression, so there is no unit column at the end. And we also further assume all the features are centered. So in other words, uh, for example, if you have the x11, x12, suppose we have two features, xn1, xn2, okay? So all centered means if it's not centered, we just subtract from the each x from each column. We can calculate the sample mean of x1 bar. We can also calculate the x2 bar. Okay, we centerize, so which means we have each column x11 subtract x1 bar, xn1 subtract x1 bar. Okay, x12 subtract x2 bar, xn2 subtract x2 bar. Okay, so that's what it centered means here. So each column we subtract from its average, we shift by the average. So therefore, for future x, all the columns summation should give you 0. So if you summation I from 1 to n, if you summation all over all samples, for the jth feature, you should get 0 for all j. Okay, so to derive the principal component vectors, what we need is we need the mathematical concept called orthogonal projection. Of a point x onto unit vector w is given by x tilde equals to the inner product of the x with w multiplied by w. Okay, so what's that mean? So for example, if we have a point, suppose we have a vector, suppose w here is a unit vector which is denoted by 1 over square root 2, 1 over square root 2. Okay, suppose now we have a point. Suppose x is a point. I think this x should be a little bit lower suppose we have a point x. X is here. X equals to 1, 0, 1. So this is the point. So orthogonal projection from this point to the vector x. What's that mean? So which means if we're starting this from this point, we find a perpendicular line and the intersection point. So this is called x tilde. Okay, so how do we find this x tilde? The formula is given here. Okay, for example, we can first find the dot product of x with omega, which is given by 0, 1, multiply 1 over square root 2, 1 over square root 2, which is equals to 1 over square root 2. Okay, and then x tilde will equals to x omega multiply w, which is equals to 1 over square root 2 multiply square root 2, 1 over square root 2, which equals to half. Okay, so therefore this point is just has coordinates half. Okay, so this is called orthogonal projection of a point x onto the vector w. Usually in the following we assume this should be unit vector. In the following, we assume w is unit vector. For example, like this w, the length will equals to 1. Okay, if not, we just use the formula will be given by again we still use x inner product with omega with w, multiply with w, but you want to divide the length of the w to normalize the w. Okay, but in the following we assume, so we're gonna use this formula. So the idea is that we are going to pick the best direction w, that is project all the data down to the w, so we can analyze it in a one-dimensional space. Of course, we're gonna lose some information when we project down from the high dimension to just one dimension. But suppose we pick several directions and span the subspace, and that subspace is a principal component, actually. Yes. Okay. So now this is just a point projection to one vector. Suppose now we have the given a point, given orthogonal orthonormal directions v1 vk. Okay, so what's that mean? Suppose we have the 3D space. Suppose this is a xy plane, this is the xy plane. Suppose this is x, this is x1, this is x2, this is x3 axis. Now suppose in the x1 x2 plane, okay, maybe let me draw a little bit more here, and we have an orthogonal vector, which means suppose we have another another normalized vector, which means we have a subvector in the x1, x2 plane, but they are orthogonal, so which means they perpendicular to each other, and orthogonal, which means each of them are also unit, also a unit vector. Unit vector, but also orthogonal to each other. So we call this V1, V2, okay? V1, V2 lives on the x1, x2 plane. So now suppose we have a point x. We have a point which has 3 coordinates, right? So now what is the, so this V1, V2 also spans a space, right? Spans a space. So what's the projection? What would be the projection? What would be the projection? What would be the projection of this x onto this V1, V2 coordinates? In other words, we want to project this one to the plane, but we wanted to find the coordinates in the V1, V2 system. And this is perpendicular to this one. This is perpendicular to this one. Okay, so in other words, what's the coordinates here and what's the coordinates in the V1, V2? So the answer is given by here. So the projection x tilde. So x tilde lives on the V1, V2 space. X tilde, okay, will equals to. So originally this has 3 coordinates, right? x1, x2, x3. So and now, so d is equal to 3, k equals to 2. We have v1, v2. So I is from 1 to k. So what we do is we find the projection of the x to each of the vector vi and multiply by the vi. Okay, so that's the coordinates. That's the vector x. That's the projection x. And this is also called the principal, the k, because we have k. The k principal coordinates. The x dot product with vi in the principal component space. Okay. So now let's see how do we use this projection to find the principal component space. Okay, so that's the math preparation we have, orthogonal projection. Okay, so now we are ready to derive the principal component. So so once we have design matrix, so we use the x transpose multiply x. This is so once we have the observation with design matrix transpose times x is always a square matrix. Because remember what's the dimension of the dx is the n times d, right? Transpose is d times n. So this together will be d times d matrix. So this is a square matrix, and it's also symmetric. Positive definite. Positive definite means, recall that positive definite means we have the eigenvalues at least part B are all non-negative, non-negative. So the smallest eigenvalue, the second smallest eigenvalue, the largest eigenvalue. So they are all positive, non-negative. Okay, so we let this to be the lambda 1, lambda d be sorted eigenvalues. Okay, so since this is positive definite, we can use the algorithm to find not only find all the eigenvalues, we can also find the corresponding eigenvectors. Corresponding orthogonal unit eigenvectors. So actually, these eigenvectors are also principal components. Okay, and the most important component will be the largest, the eigenvector, unit eigenvector corresponding to the largest eigenvalue. Okay, so in the following, I will derive 3 ways. I will show VD is the most important principal component. Okay, so VD is a eigenvector corresponding to lambda d, the largest eigenvalue. Okay, so method 1. Okay, the first method is so method 1 to find the principal component is to fit a Gaussian distribution to the data. Via the maximum likelihood estimator. Okay, and choose the first k Gaussian axis. With greatest variance. Okay, so here I have a graph here. So for example, in this data set, we have suppose every data has two coordinates, two features, x1 and x2, okay? And we can fit the Gaussian distribution. Remember, Gaussian distribution corresponding to this ellipse-shaped contour plot. And this is the average, this is the mu1, mu2. Okay, actually, the direction of the Gaussian distribution with the largest variance will be our first component. So actually, as we can see, this direction, the variance is bigger than the second direction. So this is the first component. Okay, this is the second direction. So therefore, the first method to find out the principal component is PCA algorithm. Okay, so you center the x. You center your feature space, and then you compute the unit vector, eigenvector of x transpose x, okay? Because in normal distribution requires MLE for the normal distribution of covariance matrix. Is nothing but the sigma hat equals to x transpose x divided by n. Okay. Okay, once you calculate all the eigenvectors, you choose a number k. In a minute, I will explain how do you pick a k. You pick a k, and for the best k dimension subspace, pick eigenvectors. So suppose we just sort the eigenvalues, and we find the largest k eigenvectors corresponding to the largest k eigenvalues. So it's d minus 1, k minus 1, okay? V d k minus k. D minus k, okay? Vd. So we pick the k of them, okay? We pick the largest k. We pick the k eigenvectors corresponding to the largest k eigenvalues. Okay, and then you compute k principal coordinates. Okay, so that's the projection of the all points to the lower dimensions. So in other words, which is x inner product with vi for each training or test data. Okay, that's the end. Okay, so here the first question is, how do we pick a k? How do we determine, because there are at most d of them, right? So there is a plot here. I want to show you. Okay, actually it's corresponding to, we pick the k corresponding to the percentage variabilities, because we want to pick the direction that the data varies most, right? Do you remember the first plot here? If you think if you check the, oh, this plot, right? So this direction varies most. So, but for example, in this, in this example, the x-axis is the number of the eigenvectors included, and the y-axis corresponding to the percentage variability captured, which is calculated by the overall eigenvalues, which is divided by the first k component eigenvalues. For example, in this example, the original, we have the 17 up to 17. So we have the 17 features. Okay, actually up to the seventh, if you include 7 features, so this means your principal space could capture the up to 90% of the variations. So in other words, we reduct our, if we wanted the 90% variation, we only need to use the 7 transformed features. Okay, if we want to use 4 of them, we can still capture 80% of the feature variance. So that's how we do the dimension reduction. So here, this is how we pick the number k. And there is one real data example. Actually, there is here is one example from our textbook. I think I need another plot, which is, I'm waiting here. Okay, maybe I cannot find that picture. Maybe I can just use this one. This plot shows the US arrest data. Okay, so this is the US arrest data. So in this data set, we have the criminal record for each 50 states, and the data set contains, for example, four variables. The first is the number of the arrests. Okay, the first variable is the x1. The original feature is x1 is the number of arrests per 100,000 people. Okay, and the x2 variable is the assault. Murder X3 is a variable murder. X4 is another feature rape. Okay, so which means each dot is a point. Each point is a state. Okay, for example, each is a state. For example, the Texas. We have for example, we have some number of the. We have some number here, so it's the number of the arrests. This is also number of the assault per 100,000 people, number of the murders per 100,000 people, number of the arrests due to the rape per 100,000 people. So originally the feature space has 4 dimensions, so it's hard to visualize, right? But now this gives us a principal component for the first 2 principal components. For example, we have the k equals to 2 principal components. And each data point here corresponding to the so each point xi times v1. Okay, and we have the second coordinates is xi times v2. v1, v2s are eigenvectors from the v1, v2 are obtained from this X transpose X matrix. Okay. Okay, so this example, so what's this Brown lecture arrow represents? This represents eigenvectors. Actually, once you obtain the design matrix transpose design X, you can find all the eigenvectors, right? So you find the first principal component vector v1. So in this example, we have, if you check the textbook, it's on the table. It's on table 12.1. Okay, so this first eigenvector is 0.53, 0.58, 0.27, 0.54. Okay, the second orthogonal vector is negative 0.41, negative 0.18, 0.87, 0.16. So this arrows is also called the loading vector. For example, the first is the murder. The first data corresponding to murder. So the murder arrow, so the first coordinate is positive, second coordinate is negative, negative 0.41. So these are how we get these loading vectors. And we can see that from the first direction, this rape vector and this assault and the murder, these 3 variables, the first coordinate are similar. Similar. So which means probably the first component corresponding to the overall rate of the crimes. So the first component. So this means first component corresponding to criminal rate. all we can say is crime rates. Crime rates. And the second component, where the urban population has the largest. So the second component may be related to the population who live in the urban area. Actually, now we have this plot here. Actually, I want to show you this plot too. So actually, if we take a close look at the California, Nevada, and Florida, these three states has the largest first component, first component. Probably it because these three states has a higher crime rate. Okay, and also California and New Jersey, these states also have higher urban populations too. So because you can see, and also some other states like Mississippi has the lowest urban population. Okay, and we have also few states like in Maine, New Hampshire, Iowa. These states probably low crime rate. Because it has low values in the first component. Okay, so in this video, I just give you one example how to implement this PCA principal component, and I give you one examples how to interpret these results.